In this video, we're going to take a look at a couple of different centers of a triangle. To start things off, we need to know how we can cut different sides or angles of each part of a triangle. So we're going to first look at a perpendicular bisector. This will be anything that basically cuts a segment in half and does so at a right angle. So here in this picture, that red line is perpendicular to AB, and that point is supposed to be that midpoint. So that red line would be that perpendicular bisector of AB. Now, there's a theorem that's associated with this. It turns out that if you connect A to any point on that red line and then B to the same point, you're always going to get the same length. So that theorem would say any point on your perpendicular bisector is equidistant to the endpoints. So here I just chose that point C. When you connect A to C, that would give you the same length or distance as connecting B to C. So this basically says if on perpendicular bisector, then equidistant to endpoints. The converse of that is also true. If you can find a point that is equidistant to both of your endpoints of your segment, that has to be on your perpendicular bisector. So both things cause each other to happen. Now, looking at some centers of triangles, we're going to see how this makes a connection there. First, we need to know a point of concurrency. So whenever you have multiple lines, more than just two, and they all intersect at the same point, we call that a point of concurrency. So here, point A is a point of concurrency. And there are different types of points of concurrency. There are 4 of them that we're going to look at in this chapter. The first one is called the circumcenter. Kind of a funny name there. This is the point of concurrency you can find if you draw the perpendicular bisectors of each side of a triangle. So if I found the midpoint of AB and then drew a line through that at a right angle and the midpoint of BC, et cetera, they're all going to meet at this point D, and that's what we call the circumcenter. Turns out if you connect D to any one of your vertices, so this is a theorem, you always get the same length. So A to D is the same as B to D, which is also the same as C to D. So that's our first point of concurrency and one theorem that goes with it. So there's an equation at the bottom, AD equals DB equals DC. That's for circumcenters. The other point of concurrency for 5.1 is called the incenter. So this is whenever we cut the angles of a triangle in half. So if you bisect angle A, and you bisect angle B, and you bisect angle C, turns out all 3 of those bisectors are going to meet at one single point. That's going to be called D. That's our incenter. This also has a theorem associated with it. If you draw the distance from D to each side, which you should remember is drawn at a right angle, all 3 of those lengths are going to be equal. So D to E, D to G, and D to F are all going to be the same length. That should do it for 5.1.